So, in the last lecture we have seen how to derive an approximation for a first derivative of any order of accuracy. For example, we have derived here an approximation for the first derivative at I of third order accuracy involving 4 successive values of I, equispaced values of the function u at I plus 1, I plus 2, I plus 3. This is done for a first derivative, but in a governing equations we have not just the first derivatives but also higher order derivatives. For example, we have second derivative. If you have a derivative like dou square u by dou x square and we have to derive a finite difference approximation for that at that particular point I, then it is pretty straightforward. We can we can write this second derivative as d by dx of du by dx at I, and now if you call du by dx as a function f, for example, df by dx at I can be written as du by dx at I plus half minus du by dx at I minus half divided by delta x. Now at this stage we are evaluating u only at I plus 1, I minus 1, I plus 2 like that. We are not actually evaluating at I plus half. So we shouldn't be writing it like this, but fortunately this is not for u, it is only the value of u that is being evaluated at the grid nodes. So we are not yet evaluating u, so we can write this approximately using central differencing, because the derivative du by dx, which is our f, okay, which is whose derivative df by dx we want at I, is being evaluated as function f at I plus half minus function at I minus half. So that is on the right side, on the left side of the point I, divided by the distance, spatial distance between I plus half and I minus half is delta x. So this is one way of expressing d by dx of f at I, where f is du by dx. So we are writing d square u by dx square as d by dx of du by dx, and then we can write this approximation. This is a central difference approximation. Now this du by dx at I plus half, which is midway between I and I plus 1, can again be written in the form of central differencing involving values to the left of I plus half, which is ui, and to the right of I plus half, which is ui plus 1. So you can write this as ui plus 1 minus ui divided by the distance between I and I plus 1, which is delta x. So this whole thing is an approximation for du by dx at I plus half. Similarly, du by dx at I minus half can again be represented using central differencing around the point I minus half. So that is, to the left of I minus half is ui minus 1, to the right of I minus half is ui. So ui minus 1 divided by delta x. So this whole thing is the approximation for du by dx at I minus half, and this whole thing is divided by delta x, so we have this divided by delta x. Now if you then expand this and then bring them together, then you have a formula d square u by dx square at I as being given by ui plus 1 minus 2 ui, because our delta x is the same, and you have minus ui here and minus ui here. So you have minus 2 ui plus ui minus 1, this minus and this minus together will give you plus, like this, and this is an approximation for the second derivative at point I involving points ui and the point the value of u at a grid point to the left of I and to the right of I. So ui plus 1, ui minus 1 and ui. So this is a symmetric difference formula, so our central differencing formula for dou square u by dou x square at I. And in deriving this we have not made anything about Taylor series and all that. So what is the order of accuracy for this approximation? If you want to do that, then you are writing it like this. You can express ui plus 1 in terms of Taylor series expansion around point I. You can also put ui minus 1, expand it in terms of ui and derivative set of u at I and all that around point I, and then substitute them into this, and then you will see that the difference between this and the right hand side, which is the truncation error, is of second order accuracy. So, through a Taylor series expansion, just like the way that we have used here and substituted this in order to get a formula of this type, now we are going from this formula and substituting into this, and then see what are the terms that are coming here, and then what is the leading term that is left out. And so, in a reverse way, we can find out the order of accuracy for any given finite difference approximation for any derivative. So, we can do that, and it is a fairly straightforward thing to do. So, Taylor series evaluation of equation 12 shows that the approximation is of second order accurate, and therefore, we can write dou square u by dou x square at I equal to ui plus 1 minus 2 ui plus ui minus 1 divided by delta x square plus terms of the order of delta x square. So, this is a second order approximation for a second derivative. And what we would like to point out here is that this central difference approximation for the second derivative requires 3 points, that is the evaluation of u at I minus 1, I and I plus 1, whereas for the first derivative central difference required ui plus 1 and ui minus 1, only 2 neighboring values. Okay. So, we can also have other formulas for higher derivatives. It is just not necessarily that this is the only way. For example, when we are at the edges of the domain, then we may not be able to use central differencing, because there may be no point, no grid point to the left of I, the point where we want to evaluate, or there may not be anything to the right of right side of this. So, in such a case we would have to go for one sided differencing. Okay. So, we are going back to the same old dou square u by dou x square at I, and it is being written as d by dx of du by dx at I, and that is written now using forward differences. Okay. So, that is du by dx at I plus 1 minus du by dx at I divided by delta x. This is a forward difference approximation of d by dx of du by dx at I. Okay. So, for example, here you have I and you have I plus 1 and I minus 1, and the distance between the two is delta x. Earlier we had this one at I plus half and this one at I minus half, so that we made it central. Now, we are making it forward here. Now, du by dx at I plus half can again be evaluated using forward differences at I plus 1 as ui plus 2 minus ui plus 1 divided by delta x. So, this is a forward difference approximation for the first derivative at I plus 1, not at I. Okay. Similarly, this expression here can be evaluated using forward difference as ui plus 1 minus ui by delta x. So, that we know. Okay. So, the difference between this and this is that this is being evaluated I plus 1, therefore, we substitute for I here as I plus 1. So, I plus 1 that gives us I plus 2 and I plus 1 here. So, this whole thing divided by delta x square, and when you simplify this you get a different approximation. Dou square u or d square u by dx square at I is given as ui plus 2 minus 2 ui plus 1 plus ui plus 1 plus ui divided by delta x square. And you can go through a Taylor series expansion, or you can say, okay, I have used consistently forward difference here and forward difference here. So, therefore, the whole thing is going to be first order accurate, or you can do that, or you can formally expand this in a Taylor series expansion, and then demonstrate that this is only first order accurate approximation. So, compared to the previous one, where we have a second order accurate approximation for the second derivative at I involving 3 points here, but these 3 points are spread on either side, here we have 3 points again, but all the 3 points are to the same side of ui. Therefore, this can be used, for example, at a left boundary where you have ui minus 1 is not brought into picture. So, a central second order scheme for the third derivative needs 4 points. So, what we have done here for the second derivative, we can also do for a third derivative, and one can derive using similar kind of arguments. For example, writing d3u by dx3 at I as d by dx of d square u by dx square at I, and then substituting the formulas there. So, in that way you can do that, and then you can come up with a formula like this. And or you can also put this as aui plus 2 bui and all that thing, and then we can try to evaluate the coefficients a, b, c, d by comparison, just like we have done in the previous lecture, and then come up with the coefficients here. And you can see that here we again have, for the third derivative at I, we have a second order accurate approximation involving 4 points, I plus 2, I plus 1, I minus 1 and I minus 2, and you have I minus 1 and I plus 1 and I minus 2 and I plus 2. So, that is symmetric around point I, and that gives us a second order accurate approximation. So, we can see that as you go from second derivative, second order approximation, you have 3 points here, and here you have third derivative at the same point, second order accurate, and you have 4 points here. So, the number of points which appear in the finite difference approximation increases as either the derivative order of the derivative increases or the order of accuracy that is demanded increases. Okay. And it also depends on whether we are using one-sided or two-sided formulas. So, there is a general formula that can be derived, that if p is of the order of the derivative and q is the order of accuracy of the finite difference approximation that is desired, and n is the number of points that appear in the approximation, then n is equal to p plus q minus 1 for central differencing formulas, and it is equal to p plus q for one-sided formulas. So, if you fix the value of n, then a central scheme using the same number of points will be more accurate than a one-sided scheme. And if you want more accuracy from the one-sided formulas, then you have to use more number of points, and more number of points will slightly make your matrix bigger and make the computation slightly higher. Okay, but otherwise that's it's about the same thing. And I would also like to point out here, you have these coefficients 1 minus 2 plus 2 minus 1, and this all add up to 0 here. And again here you have coefficient of minus 2 here, plus 1, so they all add up to 0. So, in all these finite difference formulas on these uniform grids here, we get something like this. Okay. Now, what we have done for the second derivative and third derivative, we can also do for a mixed derivative. What we mean by mixed derivative is, for example, a term like dou square u by dou x dou y. Okay. So, since mixed derivative requires at least 2 variables x and y here, independent variables, we are now talking about a partial derivative dou square u by dou x dou y at point ij. Okay. So, we are looking at a 2-dimensional grid like this. You have x direction, y direction, and you have delta x, delta x. In this case it is more generic with non-uniform spacing here, but the coordinate direction xi here, all these points have the same xi and all these points have the same yj, and the intersection of these defines the point ij here, and this is coordinate line having yj, yj plus 1 and yj minus 1, and I plus 1 and I minus 1 coming here. And so, the thing which is surrounding this is given here. You have point ij here, and so if you have a formula which we will see involving these 4 points, then you have a computation molecule like this. So, we are looking at variation of u in this 2-dimensional space, and we are specifically looking at a mixed derivative like dou square u by dou x dou y, and at point ij, because there are 2 indices here, 2 independent variables x and y, spatial variations, then we usually give I for the index in the x direction and j for the index in the y direction. So, using that we can put it like this, and now we can write dou square u by dou x dou y, assuming continuous function and all that. We can write this as dou by dou x of dou u by dou y at point ij. Okay. So, now we can evaluate this function here, which is the variation of this function in the x direction. So, we can write this as dou u by dou y at I plus 1 minus dou u by dou y at I minus 1 by j. Okay. So, we are evaluating this function here in its the x derivative of this function. So, x derivative means that here we are using central differencing. So, we are putting it as I plus 1 and I minus 1. In all the cases j does not change, because we are evaluating the x derivative. So, this is a central difference approximation of dou by dou x of this function at point ij, and because I minus 1 and I plus 1 are separated by 2 delta x, you have divided by 2 delta x here. Now, we can write this dou u by dou y at I plus 1 j. We can again evaluate this using central differences, and this time it is a variation with respect to y that is being evaluated. So, we can write this as u at I plus 1 j plus 1 and u at I plus 1 j minus 1 divided by 2 delta y, and in both cases I plus 1 remains constant, it does not change, okay, because it is a variation with respect to y that is being evaluated, and again here it is a variation with respect to y, but at I minus 1. So, you have u I minus 1 u I minus 1, and it is a variation with respect to y. So, you have j plus 1 and j minus 1. Again j plus 1 and j minus 1 are separated by a distance of 2 delta y. So, you have 2 delta y here. Now, you can simplify all these things, and you could be getting an expression as given here, u I plus 1 j plus 1 minus u I plus 1 j minus 1 u I plus 1 j I minus 1 j plus 1 plus u I minus 1 j minus 1. So, you have I plus 1 j plus 1. If you now go to this particular thing here, so we are evaluating dou square u by dou x dou y at this particular point ij here. For this you have I plus 1 j plus 1 is this point, and you have I plus 1 j minus 1 which is this point here, and you have I minus 1 j minus 1, and you have I minus 1 j plus 1. So, the 4 corner points are being evaluated, are being used to evaluate this function, whereas when we had dou square u by dou x square or dou square by dou y square, we make use of only these immediate neighbors here, not the corner points. So, the computation molecule for the evaluation of dou square u by dou x dou y, the mixed derivative, will bring in the corner points, whereas if you evaluate the second derivative of u with respect to x or y, if you are evaluating this with respect to x, then it is the 2 immediate neighbors to the left and right will come. If it is dou square u by dou y square, immediate neighbors to the top and bottom will be coming here. So, there is a difference in terms of what neighboring molecules we introduce to come up with a corresponding evaluation approximation for a derivative. So, this particular feature of mixed derivative, so that is it is bringing into play the corner points and not the immediate neighbors, and also the fact that dou square u by dou x dou y, the approximation here does not involve the value of u at ij, is again a potential problem for us when we consider the whole discretized equation, but we will get to that later on. So, there are a large variety of approximations that are possible for a given derivative and for a given order of accuracy, and so we can say that at this stage we know for any derivative that may be appearing in our partial differential equations, we can develop a corresponding finite difference approximation of a given order of accuracy. Now, at this point I would like to mention that in our Navier-Stokes equations that we have written for a Cartesian coordinate system, there are no mixed derivatives. We have only normal derivatives. For example, dou square u in the x momentum equation, you have dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square times viscosity is the viscous diffusion term that appears. So, it is always dou square u by dou x square or dou y square or dou z square. So, only the normal derivatives. We do not have dou square u by dou x dou y, but if we do a coordinate transformation from an orthogonal coordinate system like Cartesian coordinate system or cylindrical polar coordinate system, from that kind of orthogonal coordinate system to a non-orthogonal coordinate system, which may happen in some special cases when we are dealing with complex shapes. In such a case we have these mixed derivatives that appear. Otherwise, in our Navier-Stokes equations we only have normal derivatives and the mixed derivatives do not come into picture. Okay. So, with this we can claim that we are now in a position to write a finite difference approximation for any derivative, and therefore we are in a position to come up with a discretization scheme for a given differential equation. So, in the next lecture we will do a tutorial on a Poisson equation. It is very similar to what we have done in the very first week, but we will do it again with different boundary conditions just to test our understanding and also to put our knowledge of being able to derive any approximation for any derivative. We will put that into test in the form of a tutorial. That is in the next lecture. Okay.